we're going to define electric potential energy, PE, in the similar manner to gravitational potential energy. What was gravitational potential energy? It was how much energy it took to lift something from the surface of a planet into outer space. We're going to say that electric potential energy reflects how much energy, the work, that it takes to move a negative charge from a point near a positive charge out to infinity. So here's a picture. Here's our big positive charge, and this is a planetary positive charge. Make that a plus sign. Here is a negative charge. Which way does this negative charge want to move? To the left or to the right? Sorry? Left, because unlike charges attract. So can I say it wants to fall down? So I would have to do work. I would have to be pulling. If I was moving it out this way, it doesn't want to move this way. I would have to be, I'll say, lifting. I know it's in the sideways direction, but I would have to do work. I would have to expend energy to get it out to infinity. Although, just like before, do you know how much energy you'll have out at infinity? Zero. We are going to do relative to zero at infinity. Okay? However, if these are like charges, which way does it want to move? Okay, if I was calculating how much work now, I would be saying how much energy if I started at infinity and wanted to move it closer and closer and closer. Because the closer I got towards that big positive, the harder I would have to push, the bigger the force. So part of the problem is we're going to have some way to deal with the fact that stuff can fall up and stuff can fall down. Okay. Recall that the force between two charges is not constant. It varies with distance. It's K, Q1, Q2, or big Q, little q over r squared. Recall also that with the varying force, we cannot use force times distance because the force is changing. Instead, we have to find the area under a force versus distance graph using calculus. You don't know calculus, so I'm out of luck there. I'm just going to tell you that potential energy for electricity is K, big Q, little q over R. This may look fairly similar, Braden, to potential energy for gravity, which was big G, big M, little m over R, except we had a negative there. Now, we're not going to put a negative in this one, and the reason is here we are going to include the signs. You'll notice I did not put absolute values around the Q's. And on your formula sheet, please double check that equation. I didn't put absolute values around the Q's there either. I put absolute values, Sarah, around the force equation Q's, yes, and the electric field equation Q's, because we don't put the signs in there. We do put the signs in for work and energy. And the reason is, if we have a positive times a positive, what's a positive times a positive? Okay. If you calculate how much work to get to infinity, you'll get a negative answer because it doesn't. Because it doesn't. It wants to go there on its own. If you put opposite signs in there, that's where the negative will come up and take care of itself. So, don't worry about why there's no negative there. I'm just going to say, as long as you remember, Lena, here, we are going to put the signs in, we're okay. Otherwise, it's really similar to the gravity equation. What was the gravity equation? The force equation, but with an R, not an R squared. Yeah, and a negative. What's the potential energy electrical equation? The force equation, but with an R, not an R squared. By this relationship, potential energy is zero out of infinity, because if you take the limit as R approaches infinity, you get zero. I would say that in calculus speak, but you've already told me none of you are in calculus. By this relationship, unlike charges, have a negative potential energy. The same way as you had a negative when objects wanted to fall towards each other, that will give us the same negative that when objects want to fall towards each other. Let's just dive into doing some of these. Example 1. It says, find the potential energy that a negative 75 microcoulomb charge has if it's 3 centimeters from a positive 120 microcoulomb charge, right there. Okay. Lyndon, what does example A want me to find? Potential energy. Gravitational, did they give me a mass in the question? Sure, no. Did they give me charges?
Yeah.
Electrical potential energy. You might want to notice where it is on your formula sheet, but I think on your formula sheet I wrote K. Did I write Q1, Q2, or did I write big Q, little q?
Q1, Q2.
Okay, they're interchangeable. I'll go big Q, little q over R. Lyndon, what's little k? It's a nice constant. I know you've forgotten over spring break, but you know where to look now. Good. Nope.
Good job.
Where is it? Did you find it? It's in your constant section.
It's right underneath that.
Right underneath big G. Is he on the right page, Manir?
Yeah. Oh, yeah.
Yeah.
Yeah. 9 times 10.
Yeah. And by the way, I did that on purpose. I don't mind letting you struggle. You need to remember where, you know it's on there, find it. Again, you'll have it memorized by the test, but by June you'll have forgotten it, you know where it is. Big Q, I'll call that the planetary charge, the bigger charge there. So I'm going to go positive 120. And then what did we replace the microcoulomb with? 10 to the what? Negative 6, right? Do I have absolute values around the charges? Okay, so I'm going to include the sign. Negative 75 microcoulombs all over 0.03. 0.03 squared? No. How many joules of energy does that system have stored up in it? You are going to get a negative answer. Don't freak out. Negative 2,700? Okay. Units, it's energy. Check your powers of 10, by the way, kiddo. Yeah. Joules, direction, Lyndon. Trick question. What do you know about energy? Direction? Scalar. Yes? Scalar. So no direction here, much like your future. Yeah, he's going to take that. I have control over his grade still. Kyle, what's B want me to write? Work is the change in potential plus the change in kinetic. Now, I got to be honest. Work energy equation, sometimes I write that, and sometimes I write the law of conservation of energy. How did I know which one to do? I read part C. What does part C want me to find? Okay, so I wrote down the work equation. If they had said, find a radius or find a speed, I'd probably have written down kinetic initial plus potential initial because kinetic final plus potential final. And I think in this case, looking at the picture, I think I can do that. I don't see any indication that we're not at rest. Is that okay? What's changing anything, Kyle? So this is going to be PE final minus PE initial. Now, in our diagram, Kyle, initial is right here, and final is out at infinity. Oh, out at infinity, what's my final potential energy then, by definition? Oh, that's nice. I'll take that. Minus, what was my initial potential energy, Kyle? And do you see I have a minus minus, which is a what? So I actually end up with a positive amount of work. Let's talk about what that means. I'm going to stand up. You guys can look for a second. Kyle, this 120 microcoulomb charge, positive or negative?
Positive.
What about this charge here?
Negative.
Which way does this charge want to move? It wants to fall.
Yeah.
So I would have to be pushing. I will have to do work to get it out here. So I should get a positive answer. Now, the only way I can get a positive answer if I end up at 0 is if I start out negative. So the signs take care of themselves. Don't freak out. Just be careful, but don't be like, oh, what do I do for the signs? Put the signs in, do your math carefully, look for any minuses, and it will all take care of itself, and you'll get a negative or a positive answer as you should. So by this relationship, like charges, turn the page, have positive potential energy. This makes sense because now it takes work to overcome the repulsion. In other words, if I look at this picture, if I move this 2.5 millicoulomb charge towards this other charge, as I get closer and closer, they're repelling more and more and more, and I have to do more and more work. But it is definitely a changing force, so I can't just go force times distance. But Lena, as long as I'm careful with my signs, I'm okay. Lena, what's example 2 want me to find? Did you say find the work? Yeah. Don't overcomplicate it. What does it want me to find? So we're going to go work equals change in potential plus change in kinetic. And Lena, I don't sense any speeds here. Oh, you know what? It says assume it begins and ends at rest. Okay. Lena, what's change in anything? PE final minus PE initial. Now, in this case, Lena, unlike the last question, initial is out at infinity and final is there. Oh, did I say out at infinity? What's our initial potential energy? Okay. Work is going to be PE final. What's our potential energy for electricity equation, our electric potential energy equation? I think you're right. I just couldn't hear you. Yep. Big Q, little q, or Q1, Q2. I don't care which version you decide to go with. And I'm going to include the signs. So if these were both negative, I would have a negative times a negative, which is a. If they're both positive, I get a positive times a positive, which is a. This is why I said the signs will take care of themselves if you stick them in. So, Lyndon, what's K?
9 times 10.
Thank you. Charge 1, is this fixed? Oh, it's milli. It's not microcoulombs. It's millicoulombs. From your formula sheet, what do I replace a milli with? 10 to the what? Is it -3? Yeah, and you know where to find that? So I'll almost always use microcoulombs. Once in a while, I will use millicoulombs. And then it's going to be 2.5 millicoulombs divided by, and our final position. And you can see, Lena, if you don't understand that we're defining infinity to be 0, this is a terrifying question because kids are always, well, what's this distance right here? I don't care. I started out with no energy. This is also, again, why we defined gravity out to infinity to be 0 as well, to make the math easier. And because we have to have a reference somewhere. What do you get? How much work?
In math.
7,875? So I'll go 7,880 if I go to 3 sig figs, but whatever. Lena, units, work at energy. Joules. Lyndon, direction? No, is none. Yeah. Okay. That's how much energy, though, it would take to move that charge from, and by infinity, what I really mean is really far away to that location. What if I started out with the charge in this location and let it go? What would happen? Really? They'll attract each other?
Are they, or am I blind? Oh, never mind. They would go away.
So if this is fixed, that's why it says a fixed charge. If this is glued to the page, what will this one do? Move which way? What would happen to its speed? as it goes away. I think it's going to be speeding up, speeding up. Now, the force gets weaker, so its acceleration gets smaller, but it's going to be accelerating the whole way. I wonder what its final speed would be. That would be a job for conservation of energy, G. Okay? We'll look at stuff like that, too. So, for a scalar, for energy, we will include the positive or the negative sign in the equation, unlike forces and fields, both of which are vectors, where we decided the direction ahead of time by using either like repel, unlike attract, or for electric field by saying, which way would a positive want to move if it could? Now, if there is no external agent, so in this question we had who was moving these charges around. You can imagine, Kevin, a little invisible leprechaun or something like that. Something was. If they're just moving on their own, that means energy is going to be conserved, and we can use conservation of energy, G. I like example 3. I like example 3. Example 3 is a nice question. Kevin, it says this. An electron is originally 2.5 times 10 to negative 11 meters from a proton and at rest. I would probably underline the word at rest. It's released and it moves directly towards the proton. Find its speed when it's that far from the proton. First of all, would it move towards the proton? Why? Because unlike charges, would the proton move towards the electron? Not in this picture. I said it's fixed to the page. That means it's glued to the page. You know what? I'm going to argue, Mitra, this right here is the same physics as dropping a ball to the earth. You're going to start out with some potential energy, and it's going to turn into kinetic energy. The only problem is I don't think my final potential is going to be 0. This is a job for the law of conservation of energy, G. So, kinetic initial, potential initial equals kinetic final plus potential final. Are any of these 0? Yep. Is PEI or PEF ever 0 in this question? Only if we were at what location? Out of infinity. We're not. If I wanted to make the question easier, if I wanted to make the question look harder, but actually end up being easier, I would let you start out at infinity. You'd be able to cross out one of those terms. But I was mean. Okay. It's going to be K Q1 Q2 over R initial. That equals a half M V final squared plus K Q1 Q2 over R final. What am I trying to find? I probably could get the V by itself, but just like back for gravitation, I'm not going to bother. You know what? I'm going to move this to that side. I'll get K Q1 Q2 over R initial minus K Q1 Q2 over R final. That equals a half MV squared. And then once I get this, Lena, as an answer, I'll times by 2, divide by M square root. But I'm not going to try and get the V by itself right away. Lyndon, what's K? Q1, it's a proton. Someone said it here.
1.67.
Nope. 1.67? That's a mass. Why would you say that was a charge? That's kilograms. How dare you? Q1, it's a proton. What? Why would it be 2 times the elementary charge? Yeah. 1.6 times 10 to the negative 19. Charge 2. It's an electron. It's not the same.
It's mass of an electron.
Negative 1.6 times 10 to the negative 19. All over. Our initial. How far away were we when we started? 2.5 times 10 to the negative 11? Yes? Minus. Hey, Don't write this down. Lyndon, what's K?
9 times 10 to the 9.
What's Q? What, Sarah, what were you suggesting? Yeah. What's R final? I put it in the question there somewhere, didn't I? Is it 1 times 10 to the negative 11? I can't remember. Yeah? That's going to equal a half mv squared. I'll tackle that right side later. Okay. Now, you can see this is also really similar to gravity, except the numbers are a little cleaner. It's a lot easier to type 9 times 10 to the 9th than 6.67 times 10 to the negative 11. But it's the universe we live in. 1.6 times 10 to the negative 19. Oh, I missed the times, Mr. Duick. Times negative 1.6 times 10 to the negative 19 divided by 2.5 times 10 to the negative 11, not squared. For the first one, you get negative 9.216 times 10 to the negative 18. And I'll write down the whole schmear because 4 sig figs is easy to carry. If you didn't get that, you probably made a typo. Negative 9.216. Negative 9.216 times 10 to the negative 18 minus backspace 1.0 times there. Negative 2.304 times 10 to the negative 17. That equals a half mv squared. I'll type the first number, negative 9.216 times 10 to the negative 18 minus answer button. And that will give me the lovely minus minus, which will become a plus. I'm hoping I get a positive answer here because I think my speed should be positive. I'm positive. Do I get a positive answer here? Did you get 1.3824 times 10 to the negative 17? We should all be bang on, I think, on this case because I haven't rounded off at all. Is this right, or have I made a mistake, typo somewhere? Nate, you got that okay? Eric, you got that okay? Spencer, oh, what I care, Spencer. Okay. 1.3824. Positive 1.3824 times 10 to the negative scene times 10 to the negative scene, negative 17. That equals a half mv squared. How do I get the v by itself? First, how do I get the v by itself? Times by, let's do that right now. Divide by which m? What's moving? Look at the picture. What's moving? It's an electron. Please put a mass in there. Probably has a kilograms next to it because it's a mass.
9.11 times 10 to the negative 31.
And then that gives me a v squared. Now, Caleb, how to get rid of a squared? Only at the very end. So I would go 2 times that answer divided by 9.11 times 10 to the negative 31. This answer has to be wrong because this is faster than the speed of light. Oh yeah, I forgot to square root. Now that may seem like a big answer. Electrons, they book it pretty good. You're not following electrons moving with your eyes in any ordinary, normal circumstance. Do you get 55009? In fact, I'm going to go 5.51 times 10 to the 1, 2, 3, 4, 5, 6. So, Lena, we've taken our new way to think about potential energy for electricity, but we've tied it into stuff we already knew. We're treating it an awful lot like gravity. Really, we're treating it an awful lot like throwing stuff into the air. Except, in this case, stuff can fall up. Okay. How much potential energy does the negative 1 microcoulomb possess? I think, again, I'm going to use that fancy schmancy principle of superposition. I'm going to find the potential energy between those two guys. I'm going to find the potential energy between those two guys. You can circle if you want, but it mucks up the diagram. I'm going to erase it in a second. Here's the question. Munir, do I need to find the potential energy between those two guys? First of all, do I need to find the potential energy? Does the question even need me to find that? No, because it wants to find the energy on the one. So who cares? Like, I could find the distance using Pythagoras, but who cares? Who cares? Oh, and then I'll add them together. What should I do first before I do anything else? Before I do that, and not a free body diagram anyways, because we're not finding forces. Label the charges. What was that? So let's call, you know what, let's call the one we're interested in charge 1. We'll call this charge 2. We'll call that charge 3. I don't care how you label them, Ange, but be organized. Take that 1 second, do it. So what we're going to find is the, let's not do it in red, Mr. Duke. We're going to find the potential energy between charge 1 and charge 2. Then we're going to find the potential energy between charge 1 and charge 3. And that's how I tend to write it, with little comma subscripts. I'm going to add them. All right, my potential energy equation is K Q1 Q2 over, I'll call it R12. My other potential energy equation is K Q1 Q3 over R13. Lyndon, what's K?
9 times 10 to the 9.
Charge 1, negative, we include the signs now for energy, 1 microcoulomb. Charge 2, positive, 5 microcoulombs, all over. Munir, 2 centimeters, how do I convert that to meters?
What about
So what's that going to be?
0.02?
0.02? How many joules of energy are stored between those two? I think it should work out fairly nice. It might even work out evenly or close to it. You're not going to have like 8 or 10 decimals going on. Negative 2.25? Units. Okay. 9 times 10 to the 9th, negative 1 microcoulomb, negative 2 microcoulombs, all over 0.04. Oh, wrong button. I think I got to change this to a negative 2. And then change that to a 0.04. You get positive 0.45 joules? So the potential energy that charge 1 possesses, add them up. Mr. Dewick, do I add them vectorially? They're scalars, who cares? And because earlier, I think, Munir, you said Pythagoras. Honestly, no. In fact, a classic old provincial exam question was they would give you this picture, but instead of having it be a nice right angle, they would actually draw this too long and put the charge right there. And if they really want it to be mean, they'd give you that angle theta, even though it's not needed, and they would just let kids go crazy with trig and finding components and all sorts of BS, unnecessary garbage. This would have been a nasty multiple choice. Oh, and then probably answer A would be the answer that you would get if you did nonsense trig and Pythagoras. It's one of my rants back when we did energy. One of the reasons, Lena, I said it was so nice, it's a scalar. It's a scalar. So, what's the total potential energy? I can do it in my head. It's going to be negative 2.25 plus 0.45. Is it negative 1.7? 1.8? Negative 1.8? What's that negative 1.8 joules telling me? If I wanted to move charge 1 all the way out to infinity, I would have to add 1.8 joules of work to get to 0. And that would be from an outside source. In other words, Munir, if I said, can you move that charge all the way out to infinity? How many joules of energy will that cost me, Mr. Dewick? It'll cost you 1.8 joules to get it to 0. One more. I like this question, I like this question, I like this question. It says this, an electron starts out 3 meters to the right of a fixed negative 5 microcoulomb charge. Okay, I did say DULP. So here's my fixed charge. And it is, I'll call it Q1, and it's negative 5 microcoulombs. And it says the electron is starting out 3 meters to the right. So here's charge 2. Oh, how big is charge 2? It's an electron. What is it? Quit giving me kilograms when I say how big is the charge. Okay. And I guess right now it's moving with an initial speed of 4.6 times 10 to the 6 meters per second. Now, I have to warn you, I made this question up, and I didn't solve this ahead of time. I added this to this lesson this year because I like this question, I like this question, I like this question. That's a hint. So we may get a lousy answer. I don't know. It's moving to the left. Now, as it gets closer and closer to this fixed charge, what does the electron experience? Attracting or repelling? Which means what's going to happen to its speed? In fact, I'm going to suggest there's a certain spot slowing down, where it stops and reverses and heads back out. Where is the spot where it stops? That's what this question is asking us to find. Is that okay? Is this question asking me how much work? No. Then you know what this is a job for? Conservation of energy, G. Are any of these 0? Kevin? Comes to a stop. Okay. Are any of my potential energies 0? No, I'd have to start or end where? Infinity. Now, if I wanted to make this question look tougher but actually be easier, I'd give you the same question. I'd say, out at infinity, the electron is traveling at 4.6 times 10 to the 6 meters per second. How close will it get? Also, it'd be actually easier, but it would look more terrifying. Out at infinity, what? Okay. A half mv initial squared plus mgh? No, this is electrical potential energy. K Q1 Q2 over R initial. That equals K Q1 Q2 over R final. Sarah, what's this question asking me to find? Which variable is how close it gets before it comes to a stop in my equation here, folks? It's R final. Where is R final? On the bottom. You know what? I'm going to get this as one answer first. It's a little bit of number crunching, but not too hideous. Lena's memorizing pi. Pardon me?
She already did it.
She already has. Yeah, I know.
Yeah. All of them.
You got all 50? Sometime you'll have to... 75? Places pi? I love it. That would make to me,
It's a really good part.
ATM cards should allow you to make the codes as long as you want, because yours would be almost uncrackable, right? It's all the digits of pi, but I left one out just to mess with people.
What if she hit her head or something? When she,
You could look it up online. There's a book by Douglas Copeland, Canadian author, who coined the term Generation X. He wrote one about 10 years ago. I can't remember the title, but the premise is it's four people working at an IT spot, and in the middle he has nerd games. And so there's one section where there's 8 pages of the digits of pi, but one of them is wrong. You have to find which one is wrong. And there's another section where there's, I think, 10 pages of capital O's, but one of them is a 0. You have to find which one is the 0. It's stuff like that as well, which nerds totally get into. Anyways, back to here. You ready? Manir. 0.5. M. What's moving? It's an electron. Please, I want a mass. Please look at the units. I want a mass for an electron.
9.11 times 10 to the
Manir, V initial.
4.6 times 10.
Don't forget the squared. Plus, Lyndon, what's K?
9 times 10.
Q1, that's the fixed charge. I've scrolled down. How big is the fixed charge? Negative. I didn't hear. Sorry, what was it? Negative what?
5.
Microcoulombs, which is 10 to the negative 6. It does say micro on your sheet next to that symbol, by the way. Charge 2. It's an electron. Manir. Charge in coulombs for an electron. No. Kyle.
Negative 1.6.
Which is really important because that's going to give us a positive answer here. Divided by, what was our initial? 3. That's going to equal that other thing. I'll just put ditto marks there for now. But that equals K, Q1, Q2 over R final. Okay, you know what? I'm going to try. I think this I can type in one line. A half M V squared, a half M V squared plus 9 times 10 to the 9th, negative 5 microcoulombs, negative 1.6 times 10 to the negative 19 divided by 3, not 3 squared. Double check my typing. Ooh, typo there, Mr. Dewick. Negative 5. Do you get 2.4096 times 10 to negative 15? I see one person nodding. Anybody else?
2.39.
So go check your typing. And as we said, Braden, in the gravity section as well, there's a lot of typing here. That part I can't help you with except to give you some strategies like the ditto marks, like, I've been trying to teach you really since Physics 11. I've yelled at you about getting a good calculator. Kevin finally caved. 2.4096 times 10 to negative 15. 2.4096 times 10 to negative 15. That equals, did I write that down right? 2.409 and other stuff, but I'm just ready. I'll keep the answer button on my calculator. That equals K Q1 Q2 over R final. Sarah, coming back to you. What was I trying to find? How would I get R final by itself now, folks? Times to the top and divide my answer button to the bottom. Yes? Is that okay? R final is going to be 9 times 10 to the 9th. Q1, negative 5 microcoulombs. Q2, Meniere, it's an electron.
Negative 1.6.
Well done. All over. Heck, I'm just going to write ants, because that's what I'm going to do with my calculator. 9 times 10 to the 9th times negative 5 microcoulombs times negative 1.6. Now, Meniere, also, though, if you're lazy at this stage, what's a negative times a negative? If I was really lazy, I could leave the negatives off because I'm going to get a positive answer. I leave that to your own discretion, what kind of shortcuts you want to take. Divided by answer button, and let's see if I made up terrible numbers or not. Did I? How close is it going to get? It's like almost 3? So it's barely moving before it comes to a stop. So I should have added a power of 10 to my initial velocity, I think. Okay, I'll do that for next year. 2.99. Bad mental math by Mr. Duick. I was doing this literally the Thursday, I think it was the Thursday before spring break, and I was tired, and kids were asking questions. And okay, what's your homework? Number 1, except you can cross that out. Two is good. 3 is good. 4 is good. 5 is good. Nah. 6 I'll skip. 7 I nuked apparently over the years.
9.
8B. And 10. Nine would also be forces review. We'll get there as we get towards the end of the year. I've been telling you that there's lots of energy stored in these.